Okay, so recording has started. So those of you who are joining this week's problem solving session, welcome. So I'm Ochandra Paul. I'm a PhD student here at IIT Kanpur, and I'm pursuing my PhD in the Department of Chemical Engineering. So I work in an interdisciplinary area of tissue engineering where I have been also using the principles of biomaterials. And I have also been doing various kind of biofabrication techniques as part of my thesis work, like 3D bioprinting, electrospinning, etc. If you like to know more about me, you can just simply, yeah, sorry for the network issue. So as I was saying, if you would like to know more about me, you can just simply give a Google search of my name, Mochandra Paul. Okay. So, and you will find my website and get more information about me and what work I'm doing. And if you have any technical queries related to this particular course, you can definitely post it on the course discussion forum. I have been looking at these queries and whichever I am able to solve, I will solve it there only. Apart from me, there is another TA, okay, and he will also look into your queries and help you understand the content of this course in a much better way. So these meetings will happen every Saturday. We had our last session on 27, that was the first session, and today is the second session where we'll be discussing some of the topics of week 2, and it will happen every Saturday from 4 to 6 p.m. You guys have the meeting links with you, okay? So it is also given here, and all the sessions that we are doing right now, they are all recorded, and the NPTEL people have already posted the recordings, okay, of this week. Subsequently, you will find the recording of the coming weeks as well, and the Google Drive has been shared with you where you can access this PPT that I'm using, the notes that I'm using to teach you, okay, for later. Okay, and I will be recording the attendance as well of all those who are joining today. Okay. One important note, okay. Kindly you since you guys are joining this meeting as a guest, so some options of Microsoft Teams has been turned off by default. Okay. So you guys won't be able to chat, okay, with me. So whatever queries you have to unmute yourself and ask. But if you are like keeping your mic unmute and you're talking to someone else in your home or somewhere else and creating some kind of disturbance, so I would like have to like I can ping you once or twice, and if you are not listening or responding, I will have to remove you from the meeting because I don't want to disturb others who are here to learn today. Okay. So if you have any queries during the discussion, all you have to do is unmute yourself and ask. And I want you guys to ask questions. Okay. Whatever I'm able to solve, I will. If not, I'll try my best to collect the answers so that we can discuss it in the next week as well. Okay. So first, let me like give you a revision of about mechanical properties of the biomaterials. And as you have seen, some part of the last week and some part of this week's content is based on this broad area. So whenever we are working with any type of biomaterial and we would like to understand what is its mechanical property, okay, then we do some kind of test, like the compressive test where a material is like force is given inwards to decrease its length, that is called compressive test. And from this test we are able to find compressive strength. Okay, we'll be able to find the compressive strength of a material. Similarly, we can use some kind of clamps, okay, to hold our material and apply external force to extend it. So that is called a tensile test, and the knowledge that we get out of it is the tensile strength. Similarly, we can do a bending test where the material, where the force is now applied at the center of the specimen, okay, in order to bend it. And how much is the endurance of it, like at what force, okay, it is able to bend, that is the bending strength or flexural strength. So why knowing these types of strength for a material is important? So if you're planning to make a some kind of construct or a prosthesis that will go inside the body, or maybe a tissue engineering construct that will help you to replace any organ or tissue function. So in our body, there is some kind of environment it is in, right? So it can experience some kind of compression, it can experience some kind of tension, or there will be bending motion as well. So you have to then answer a question, very important question, whether your biomaterial will be able to endure these kind of dynamic motions, and at what extent, at what is the limiting point at after which your material is no longer useful, means it will crack, okay, or it will start eroding because of all the different kind of motions happening on it. So you have to answer that to and then only your material will be able to, you know, get certification that yes, now it is safe for use in humans. Okay? That is why these kind of uh, tests become very important. So let me give you an example. Since I'm working in tissue engineering, so we work on creating artificial tissues or organs. Okay, so let's say I'm making a skin tissue. The objective of our skin throughout our life is to expand, right? So when we're little, our entire skin organ, that is the largest organ of our body, it is having some volume. Then we grow up, it becomes larger, right? So it has a tendency to stretch. When you pull your skin, it can stretch, right? So when we are making an artificial skin, the most important criteria that we have to report is what is its tensile strength, and we will do a tensile test. Similarly, if you are making a bone, artificial bone, say, and we are like replacing a very important bone in our body, which is always under say bending. So if a bone here at the arm where there is a bending motion, or when it is replaced used to replace the knee, that is a knee replacement kind of a prosthetics, there also bending kind of motion is continuously happening. So in those conditions as well, you have to justify how well your material is able to endure this kind of bending motion. So one thing to remember is these tests, the protocols that you set for these tests is already standardized, and it is standardized by a society called ASTM, American Society for Testing Materials. So whatever testing that we do, we use these standard protocols, okay, according to these standard protocols, and then only we report some values. And we have to report the protocol number, okay, protocol ID, that we have followed this particular ID for getting the values for this particular type of material. Okay, so this gives us the standard protocols to get to answer these type of questions. So now you have done it. Let's look into um, some more, say, terminologies that is related to the mechanical property of a biomaterial, but some of these properties are inherent. So a polymer or a metal or a ceramic, so it is inherent to that particular class of material. Or if you look into different kind of metals, every metal, every type of metal will have in its inherent value for that particular property. So what I'm trying to indicate is on the elastic modulus or Young's modulus. So this value of E, or elastic modulus is an inherent property. So steel or say glass, both of these have their own values of elastic modulus. Through this, we basically compare which is having more mechanical strength. Okay, and how we determine or how we define elastic modulus, this value comes from the fact that when we are applying some kind of stress to deform a material, then how much that particular material is trying to resist it. Okay, and the resistance should happen elastically. What do you mean? What do I mean by elasticity or elastically? It means whatever atoms or molecules has displaced from its original sites due to some tensile force, say, it when we release that tensile force, it will come back to its original position like a spring. Spring is an elastic material, right? So it when you expand it, it will increase in length, and when you release it, it will become shorter. So remember, elastic modulus is always defined when we are trying to um, like elastically either increases length or decreases length, means cause elastic deformation, and as a result of it, it is trying to resist it. Okay, I'll come to it a bit more when we will discuss about Hooke's law and all. Okay, then there is another specific material specific property that is called hardness. So this term helps you understand like about the material, that how much it is able to still maintain its all physical features like its length, diameter, say surface area, everything. It will maintain its physical features at what maximum at what maximum stress. Okay, so you're applying some force to maybe deform it, maybe scratch it. Okay, like you're trying to deform in some way, like change its maybe uh, polishness. Okay, it is your like you have to apply very hard force in order to polish it, in order to say etch it. Okay, so how much of that you need to do? Okay, until it is losing its like physical features, that is the hardness. So more force that you have to apply, the more material is hard. Get it? The next another material specific property is fracture strength. So this is the maximum, say, stress that the material can endure before it fractures, means breaks. You have taken a specimen, say of 10 mm, you're applying so much of tensile stress on it. Okay, that there will come a point where it will break. So that up to that, how much of that stress the material could endure, that is the fracture strength. Then another material specific property is fracture toughness. So before breaking, just before breaking, how a material breaks or how a fracture develops. It develops initially in form of small cracks, very tiny cracks. So these are called crack nucleation sites. When these sites starts forming, then it rapidly increases. Okay, it's like unlimited number of cracks starts forming, and because of which it breaks or fractures. So up to like before that point, before the formation of those tiny crack nucleation site, how much till that material was doing what? It is trying to resist that. It is trying to resist the crack formation. Until that, we are trying to define that it is that much tough against crack formation, because after the crack is like basically formed, it will break. Okay, you can there's no way you can save that material. It will break. That is the fracture toughness. So I'm trying to make you understand the essence or the meaning of these terminologies, how to calculate and all. It will become much more clear when I'll show you one stress versus strain graph. So until now, if you guys have any queries, let me know. Otherwise, I'll move on to the question part. Any query? Are you guys, have all of you understood this particular terms and what I was trying to tell you? Is it clear to everyone?
Yes, ma'am.
Great, great. Thanks for the thumbs up. Now, this is the question. The fracture toughness of a material is known from what? So the answer should be pretty much clear to all of you, but still, anyone would like to try? What will be the answer? There are four options: fracture strength,
Same.
elastic. Yes,
Crack propagation.
crack propagation. You are correct. The answer is crack propagation. We are, as I said, fracture toughness is coming from the fact that how much that material is tough enough to resist the formation of crack, and subsequently once it forms, okay, it will like spread, it will like increase in an infinitely in high rate, and that will result in fracture. So before fracture, okay, that particular quantity we are saying, or the inherent property of the material we are saying, is called fracture toughness. So crack propagation is the correct answer. Now this is the stress versus strain diagram which I was talking about. And this particular diagram in front of you is for a ductile material. Means we have taken a material onto which we are applying some tension, because of which it's increasing in length. That is called ductility. Okay. So ductility is a property, is a one of the unique properties of metals. Many of the metals are ductile, because of which we can make wires of it. So for the, so similarly we can draw stress and strain diagram for other type of materials as well, like brittle materials, like ceramics or polymers. Okay. So but for this particular discussion, I'm using a stress versus strain diagram of a ductile material. Now note this, but if you just remember this diagram in your mind, like if you have a picture of it in your mind, many of your say confusion about this particular topic will solve instantaneously. Okay. So say sigma is your strain value, so stress value, this is your strain value. And uh, say at this point, this is your state of the material when you have not applied any tension. Now once you have applied some tension on it, it's the tension means you're applying some tensile force on it. The tensile stress, corresponding tensile stress, have started increasing, as well as its length have started increasing. That is, strain value has also started to increase up to a point, up to this point, say. Now what is the significance of this particular straight line here? Now within this region, if you suppose decide to remove the tensile force, then what will happen? Your material will come back to its original dimension. Okay, it will instantaneously come back like a spring. So that is why this particular region is called elastic region. And within this particular region, we define the Hooke's law, which is nothing but stress, sorry, this is denoted by sigma. Stress is reciprocal to strain. So let me just write it again. Stress is reciprocal to strain, because within this region, however amount of stress is getting generated within the material, equivalent amount of strain is generated. So that is the Hooke's law region or the elastic region. Now suppose you are still applying your force, external force, continuing, you have not stopped, you are continuing, and you are seeing that the material, the strain in the material is still increasing, means you are still seeing that the length of the material is increasing. but but at this particular point, when you decide to say remove that, remove your tensile force, you're seeing that material is not coming back to its original dimension. The length has increased somewhat. Okay, so now you have entered what is called a plastic deformation region. Okay, so from here to here of from this point to this point of this curve is called the plastic region. Means whatever now stress that you have generated in your material have resulted some elongation, which is like not going to come back, which is like permanent. That elongation is permanent, and now it has become the new length of the material. Okay, so yeah, so we are basically making a wire, say. So there is small block of metal. You are like when you have entered the plastic region, then only from that block you will be able to make a wire, because it will now in the plastic region it will not go back and change into the dimension of a small block. Get it? So now you have entered the plastic region. So these two regions in this curve I think should be clear by now. Now here I have like marked this particular site in this graph. What is this site? So this site is called yield strength. Okay, so yield strength is the maximum stress. Sorry, I was talking about yield strength. No? So it is the maximum stress that a material has basically endured before it is transforming to become plastically deformed. So after this point, after the yield strength point or yield stress point, the material will now undergo plastic deformation. It's not in the elastic region anymore. And another quantity that people often define is called 0.2% offset yield strength. So here, this particular point is defined just 0.2% beyond the yield stress point. Okay, so here 0.2% is coming from this strain. So 0.2% of the strain has happened. So corresponding, what is the value of stress? So from that, we get the 0.2% offset yield strength. Okay, so these two are um, similar quantities. Okay, yield strength and 0.2% offset yield strength. But yield strength or yield stress is the point where the material has experienced maximum stress elastically. And after this particular point, the material will undergo plastic deformation. Okay. Now there is another quantity from this, or another piece of information that we get from this particular graph is the ultimate tensile strength. It basically means what is the maximum, overall maximum stress that the material is able to endure, maximum stress. So it is nothing but the peak. Is in this graph, what is the highest point? So correspondingly, if you extrapolate, you will get this stress value, and this stress value corresponds to ultimate tensile strength. Similarly, you can get ultimate compression strength as well. Means that is the maximum amount of tensile uh, force that the material can endure. Okay. Now we often see that after this maximum point, there is a decline in stress. Okay, there's a decline. There's a kind of it's now the amount of stress now it is going to endure is much less. It has started to decline, and means it is now going to break soon. Okay, that's why we see a decline, and the point it breaks is called the fracture point. Okay, so after this point, the material that you have used is now broken into two halves. So that is the fracture point. So if you are trying to make some wire, you have to make sure that whatever force and the corresponding stress that is generated in it has to be within this fracture point. Okay. Means, and also you have to remember that this is the maximum stress that you can generate within your material to make a wire. If you go beyond it, there's a high probability that it will fracture soon. And as I told you, the fracture toughness quantity. So we mathematically or quantify this value by getting the area under this entire curve. Okay. So if you get the area under this curve, you can define the fracture toughness as well. Okay. Any queries in understanding any of the points? I am like intentionally going a bit slow, but if you think like it's very easy, no, no, ma'am, go fast. It's totally fine. You can just tell me. Because if you are from a bio background or you're from medico background, like I've been seeing some people with doctor in front of it, maybe they are from mbbs background, so these engineering concepts becomes difficult for them to digest. So that is why intentionally I'm going slow. So have you guys understood, all of you? Because now we will do some problems. Thanks for the thumbs up. Now, this is the problem in front of you. You have to tell me in what region of this particular stress and strain curve the Hooke's law is applicable. Any one of you?
A.
Unmute yourself. A. Everyone agrees?
Yes.
Yes, correct. So it applies to the elastic region because here only we get that proportionality between stress and strain value. Okay. Now here we have a stress and strain diagram, but now I'm trying to show you that the nature of this particular plot, it varies with what material you're using. So this particular diagram is for the polymers, but various kind of polymers can show a brittle nature or it can show a rubbery nature, okay, or it means you can similarly show for metal as well, for ceramic as well, okay. So this is like what I'm trying to show is if the material is of brittle nature. So most of the ceramics are brittle. So you will see that the stress versus strain proportionality, it lasts quite long, but the plastic deformation region is very short. It breaks very easily. It is not a very tough material. Okay. Then for a rubbery kind of a material, like say a rubber only, okay, or a tire, it doesn't have very long proportionality region, which doesn't have a very long elastic region. It the nature of this material allows it to plastically deform very easily. Okay. And it like breaks also at a very later stage, like it can sustain a large amount of deformation, a large amount of stress can inbuilt, so it's a strain can happen in the material, and then it will break. But for the value of the stress that you need to break is also quite less. For brittle materials like ceramics, you need a very high amount of stress for it to break. But for rubbery materials, it's very less. But if you're working below this particular value, you can stretch it however long you want. Okay. So this is for the tensile property. That's why I'm talking about stretching and applying tension. For compression, different kind of plot will happen. Now, in these two, you can think as if for the metal as well, okay? Like for the metals, they are very elastic, okay? Uh, Means the elastic region for the metals is very long. You can see that proportionality in the curve to last for a very large value of strain. And the yield stress or the yield point value is also higher for metals. And so the previous curve, I think, should have been a much more correct representation. This one, this curve is much more correct representation of how the metal will behave in presence of a tension. Okay. And this type of material maybe say for polymers. for different kind of polymers. So what I'm trying to say is, uh, the nature of the material you are working with, they will give a different kind of stress and strain diagram. The molecular bonds between the atoms of that particular, means whatever bonds are dominant in that particular material, those will again govern how they behave in presence of an external force. For a polymer, say thermoplastic polymer, we see that at room temperature, like below its melting point, it is like a close to, not like a close to a brittle material, it will break easily. But as you try to heat it and change its structure, make it more rubbery, okay, then it will has a more tendency to plastically deform until it becomes a liquid state again. Okay, so I hope it's clear to you. And if you were given some kind of stress and strain plot and asked, like, by common sense, tell me, how, for which type of biomaterial class would you say this type of stress and strain diagram like would belong to? I think you guys will be able to interpret by looking at what, where is the yield point, how much is the value of the, so how much longer is the elastic region, how much longer is the plastic region, at what point does it fracture. Okay, so these all critical points that I told you, these will help you understand which class of the material it is from the stress and strain diagram. So this is a question for you. Here you are given some types of materials like PET, titanium, silica, and PVA. And you have to tell me which of this material will not or does not exhibit a plastic region under tension. Anyone? So PET and PVA, these are polymers. Titanium is a metal. Silica is a ceramic material. Okay, I hope that that gives you a clue. So by looking at what type of biomaterial it is, can you tell me silica? So why do you think silica will not exhibit a plastic region? Exactly, exactly. So the correct answer is, as one of your course mate told, it is silica. So silica will behave like this, that like this particular graph. It will show a very long or very large elastic region where the elastic modulus will be high, very high, but it will not blast after the yield point. It will very soon break. The elastic region, sorry, the plastic region for ceramics is very less, but for polymers the plastic region is very large. Okay, silica is a correct answer. Now we will try to do some problems using the definitions of stress, strain, and Young's modulus. So during this course we have only looked into tension and compression type of forces, but just for your knowledge, when we are working with those materials which will be in presence of some flow, okay, then shear also becomes an important mechanical property to examine. But we will not look into shear forces and what is the corresponding stress strain in today's discussion session. Okay, so for in presence of tension and compression, we can define stress and strain as follows, as given in front of you. So stress is a normalized load. So what is normalization? Normalization is a process, it's a mathematical process actually, but if you look it as a qualitative way, normalization is a way to make something or make say various kind of materials as equal so that you can compare. So if you're having biomaterial of same type, okay, two metals you have of same say titanium metal you have, but these are of different geometry. One is of spherical and one is cylindrical, and you want to like compare what is the amount of stress it is generated in both of them, or strain it is generated. So that means how much force it is experienced or how much change in its diameter or length is happening. Then you cannot do that, because a sphere, the forces that is acting on it is different in comparison to the one acting on the cylinder. That's why we use normalized quantities like stress and strain. Okay, uh, we don't compare the forces, we don't compare the change in length in quantities or in objects which are of different geometry. Okay, we use normalized quantities like stress and strain. So stress in presence of a tension and compression is given by the ratio of the force, the external force that you have applied, and it is normalized by dividing with the area perpendicular to the direction of the force. Okay, so if this is a say, cylindrical object, and the force, external force you have decided to apply in this particular direction given by my arrow, then your stress will come out to be F, that is external force that you have applied, and the area perpendicular to the direction of this force. So this is your area value, A perpendicular. Okay. Similarly, if you are say doing it in different geometry and the force is applied in this direction, then for calculating stress, you will take the area that is perpendicular to the direction of the force. Okay. Now, what is strain? Strain is nothing, again, a normalized way of saying how much the material has deformed. It is given by the ratio of how much the change in length has happened divided by the original length. So, say in this particular orientation, the force is applied in this particular direction, right here. So now the new length is, you're giving a tensile force. In both of these diagrams, I'm giving a tensile force on the object. So the change in length is this delta L, because the change in length will always happen in the direction of the force. And the original length you have to take uh, the length which is parallel to the force applied. So here the length parallel to the force is this L naught. Similarly, this is another orientation, correct? So this is your delta L, and it should be divided uh, with the original length. The original length will be the length which is parallel to the direction of the force. So that will be L naught. Okay. So if you were to say another type of geometry, so cylinder only. So you are using a cylinder only. Okay. But now the direction of the force is like this. So in this case, your area perpendicular is what? In this case, can anyone explain or can answer? If you have a cylinder and the direction of the force is now in the upward direction, then what value of area will you take for getting the value of stress? Anyone? Hello, is anyone there? Is my question clear to you? What I'm trying to ask?
Should we take the area of the full cylinder?
Okay. Anyone else would like to try? So it's very simple, no? Total surface area we won't take. We will take the circular surface area as the area perpendicular to it, this particular area. So you know from like geometry, right? You can get that area, value of that area. So that area will become your perpendicular area. Okay. Mm. And then is this case, what, how will you calculate strain? You will not take the total area, because total area of a cylinder will also comprise adding up the areas of the circular faces. These two will also, the area of these two faces will also get add up with the circular area. We are, but the force is not perpendicular to these two faces. Okay. It is perpendicular to the circular surface area. So we'll take that value. Okay. And then what will be the strain in this particular case? How will you calculate strain? Anyone?
Delta R by R.
Correct. You're correct. So in this case, what we are doing, so you can take D as well, means you can take diameter as well, because or you can take R as well. Why it will not make much difference? Strain is a unitless quantity. Okay. And the radius and the diameter, they're also in a fixed relation, like fixed ratio, right? So it's just a ratio quantity. So even if you take delta R by original R, or you take delta D by D naught, you will get the same strain value. Okay. Now I hope you have understood how you will calculate stress and strain. You have to first observe, or in the question it will be written the direction of the force. You have to interpret that. Based on the direction of the force, you will understand the area, the perpendicular to it. Accordingly, you will have to calculate the strain, or means you have to determine where the, in what direction the change in length is happening. Accordingly, you will have to calculate stress and strain. Now, if the question is saying that the material is deforming elastically, okay, and I've asked you, because of that, if the material is in plastic region, then you cannot calculate Young's modulus. Okay, if the material is deforming elastically, then only you can apply Hooke's law. This is nothing but uh, sigma is directly proportional to epsilon. Okay, and when you remove this proportionality with a constant, is this proportionality constant is nothing but the Young's modulus. So for tension and compression, you will get Young's modulus. For shear, there is shear modulus. So you don't have to worry about that right now. So uh, then Young's modulus will become stress by strain. So in this particular graph, you can see that Young's modulus you can get from the graph if you just take the slope of this linear region. If you're not given any values, you are just given this graph with values given, like this value is given, some mathematical numerical values are given to you. Okay. And you are asked to calculate what is the e value, then you just have to take the slope of this particular linear region. That will also help you get the Young's modulus value. Or if you are given the values of stress and strain, you can take a ratio of it and get the Young's modulus value. So this is the question. If you all have pen and paper with you, I want you guys to attempt it as I am doing in front of you on the screen, because I will ask. Okay, you have to do the calculation on your mobile phone or your calculator, and you have to give me answers as well. So this particular question here, it says that there's a polymer piece onto which some strain is generated due to a external force. This force is 10 Newton, and the value of strain that this polymer piece has endured is 0.015. And the original length of this polymer piece was 5 centimeter. You have to calculate what is the increase in its length in mm. So what we will do, just so this particular question is talking about a tension kind of situation where the material is under a tension. So you will think that this is your polymer piece and some tension is applied. Say in direction they have not given xyz, so that's why I'm arbitrarily drawing, say in x direction, if this is my x direction, and say in both sides the force is there in one side. You can for convenience you can just remove one side, only in one phase the force is applied. Okay, and then you have to calculate what is this delta L in this case. Sounds easy, right? Now, the dimension of the polymer, apart from its length, we don't know. We don't know anything else. Okay, that is why we cannot calculate area perpendicular to it. Now, let me ask you, do we need to? Do we need to calculate the area perpendicular to force?
No.
No. Why? It's just this value is given to you to confuse you. Okay. You just have to apply the definition of strain and you will get the answer easily. What is the definition of the strain? It is the ratio of change in length by the original length. So strain value is given to you. Original value note is given in centimeters. You are asked to report in mm. So you will convert it. So somebody tell me how much will be the value of what will be the value of delta L if you are doing
0.75 mm.
correct. 0.75 mm. Those who are not even doing it, just looking at the screen right now, maybe at the end you can use a calculator and report that. So at least from that as well, you will remember later on what you have put in your calculator, why you have put. Okay, so just try to be more involved in the class, actively listen rather than passively listen. Okay, you're here to learn, so utilize your time as much as possible. So you are correct. The answer is 0.75 mm. Now let's move on to the next question. So just give me 1 second while I drink water. Meanwhile, you guys read the question, maybe start doing the problem on your own. Okay. So in this problem, you are given a urinary stent. So stent is basically has a dimension of a cylinder. Okay, stent usually looks like a cylinder. So its length is given, its diameter is given. Length is 12 mm, diameter is 8 mm, and an outward force is applied. Outward, the force is in the outward direction. Means the force would look, direction of the force would look something like this. It is a tensile force. Okay. And what is the value of that force? It is 40 Newton. As a result of this, the material, the stent here, has gained a net elongation of 0.01 mm. Now you have to calculate based on these given values what is the value of stress, strain, and Young's modulus. Okay, you have to calculate stress, strain, and Young's modulus. So I'm using the fresh slide So stress will be the force divided by the area perpendicular to it. So in this dimension, in this diagram, area perpendicular to the force is the area of a circle, isn't it? It's a circular face. So area of the circle is nothing but pi r square. So we are given d, so d by 2 square. So anyone tell if you have done it? What is the area you have gotten? Tell me. Are you guys doing it? What is the value of area that you have got?
25.12.
25.12. Okay, just quickly check. Are you sure it is 25.12?
It's 50.24.
50.2.
50 point.
Yes, yes. 50 point.
24.
24.
Okay, okay. 50.24 mm square. Always, whenever you're doing some math problem, just write the dimension for your own, so that you don't make any silly mistakes later on. That is your area. So force, we know force was 40 Newton, area is 50.24 mm square. Then how much will be the stress value? Anyone?
0.79.
Okay, you're correct. It is 0.79 unit will be Newton per mm square. Now note this particular unit is not SI unit. Okay, but in this question we are not asked in SI unit, so it's totally fine. So we have got the answer. Stress is, let me highlight. Stress is 0.79 Newton per mm square. Now strain we have to calculate. So strain, uh, in this case, I will assume, so strain can also happen in different direction, but in this case, I'll assume that it is happening in the direction parallel to the force. Means there is change in the length. There is no change in the diameter. So the change in the length we were given, right? It was 0.01 mm by the original length. The original length was 12 mm. So what will be the value of strain then? Anyone?
0.0083.
Okay. Everyone have got the same value as him?
Yes.
Yes.
Yes. Okay, you're correct. You guys are doing rightly. Others are doing also right. So you're doing correctly. So these are the stress and strain value. Next, you have to calculate is the value of Young's modulus, which is nothing but the ratio of these two values that we have already calculated. So tell me quickly, what will be the answer then? With unit.
995 Newton per mm square.
995 again point 995 point no point. Okay, fine. 995 Newton per mm square. Is it correct for everyone else as well? Have you got the same answer as him? You guys can say that.
1.8.
Okay, 5, 9. Can 9 फिर से बोलो?
951.80.
0.80. Okay, she's getting this value. So it's close by, not completely wrong, both of you. It is nearby. So let me just show you the answer. Okay, so we have got the correct stress value. The strain value is also correct. Okay, and the girl who just answered, you are correct. You are more closer to the real value. Okay, so Young's modulus is this. Okay, so I hope every one of you have understood how we got the values of stress, strain, and Young's modulus when a particular piece of cylindrical stent was under a tensile force, and we were given some values and we had to understand how to use those values to arrive at these particular answers. Okay. Now we will understand another concept, that is Poisson's ratio. Now, what is Poisson's ratio? It comes from the fact that if suppose so this is your axis, okay, xyz axis. Now suppose you are placing a material here, and in this case you know the force is in x direction. Then what will happen? The length which is along x direction, it will increase, correct? Delta L will increase. But if you see in z direction, the direction z means the radial direction. You can see in this in cylindrical geometry, it is radial direction. There, delta R will reduce, right? So from this fact, people have determined what is means found out a quantity that is called Poisson's ratio, and it is given by Greek letter nu, and it is so for this particular geometry, nu is nothing but the ratio of strains, okay, ratio of strains, which is perpendicular to the applied force to the strain that the material is experiencing parallel to the stress. So here in this diagram, how will you write Poisson's ratio? Poisson's ratio will become epsilon in the z direction first, okay, because the force is in the x direction, divided by epsilon x. Here, strain is in the perpendicular direction to the applied force, okay, divided by the strain that the material is like strain in the parallel direction to the applied force. Now, since the changes in length causing one length, so here the length of the cylinder is increasing while the radius of the cylinder is decreasing. So those are like opposing, right? That is why a Poisson's ratio is defined with a negative sign in front of it. So as here epsilon z is nothing but a longitudinal strain, okay? Here length is increasing, whereas when under this particular force, simultaneously the diameter or the radius of the material is also decreasing, and that is here epsilon x are called the lateral strain, and it is decreasing. Okay, so you have understood how the Poisson's ratio is defined. If not, let me like show you once again. Okay. So if suppose one second, no? Like I've removed it. Now suppose you are having another piece of cylinder. Now the orientation is something like this. Now the force that you're applying is in the y direction. So now tell me, how will you define Poisson's ratio? Radial direction in this case would become what? Z, right? It is R in the Z direction. So tell me, how would you define Poisson's ratio in this case? Anyone? It's simple, no? So as I told you, it will be the ratio of strain perpendicular to the applied force. Yes, is anyone trying to answer? Okay, so it will be the ratio of strain. Yes, someone has unmuted themselves. Are you going to answer? Are you willing to try and give an attempt? How will you define Poisson's ratio then? Okay, maybe not. Maybe then you can mute yourself. Okay, whoever
EY
it is.
upon EX.
EY, EY upon EX. Why it will be EY upon EX? Okay. Anyone else? So why do you think it is EY upon EX? Okay, I'll answer. So here Poisson's ratio will become EZ by EY. Why? Because here Z is like the direction of the R here. Okay. And this direction of R is perpendicular to the force. So towards that direction, we have to take the strain divided by the strain value in the y direction. Y direction is the direction where the force is applied. Okay. First perpendicular direction one strain and then divided by the parallel direction. And again, let me just, if it is still not clear, and remember the minus sign will be always there in whenever you are trying to define Poisson's ratio. So, again, let me draw a cylinder like this. And the force here is applied in Z direction. Just quickly tell me what will the value of Poisson's ratio here then. We are applying a tensile force.
Ma'am, EX by EZ.
Correct. Minus, don't forget to include minus. It will be EX by EZ. I hope it is now clear to you how to define Poisson's ratio. Okay. Now, this is a question based on that. Uh, the force is applied in the Z direction. I've for your imagination so that you can quickly answer, I have given the XYZ coordinates. So using these coordinates, you have to tell me how would you define the Poisson's ratio now? What will be the correct answer? See, these two A and B will like you have to
D.
remove it.
C.
Okay, so let me just, so someone has said C, someone has said D. That means some of you are still confused how to define Poisson's ratio. So there is a
Option C, ma'am.
hmm?
Option C.
Option C. Okay.
Yeah.
Okay. So two people are now in favor of C. I think C must be right, but still let me explain bit. So there is a material, okay, say a spherical material towards, and on it the force is applied in the Z direction. Okay. So we have to so what will the perpendicular direction to Z in this case? Let's here Y they have not considered. So for this sphere Y is also perpendicular direction. X we will take. Okay. So X is the perpendicular direction. So Poisson's ratio will become negative of strain in the perpendicular direction, that is X here, divided by the strain in the parallel direction, that is Z. So that is why option C. Both of you who have answered option C, you guys are correct. Okay. So the Poisson's ratio in this case will be minus of epsilon. So E is used to define strain. So minus of Ex by Ez. Okay. Is it clear? The concept of Poisson's ratio, is it clear for everyone? Great. I got one thumbs up. I assume that everyone has listened. Okay. So this is another question. So it is based on one of the problems given in the lecture. Okay, it is very similar to that. So you are given a catheter tube. It is having a Poisson's ratio of minus zero point 0.6. Tube diameter, its diameter is 4 mm and its length is 100 mm. And the force is applied in the outward direction, and it is producing an elongation. So it is a tensile force. So so there is no XYZ mentioned. So let me assume that it's a tube oriented along X direction, and the force is also along X direction. I'm assuming this. So in this case, force say Fx becomes 20 Newton. Why I'm using X and Y? Because this Poisson's ratio, it will help us to determine the expression for Poisson's ratio. That is why I'm referring to X and XYZ coordinate system. The elongation that the material has experienced. So since Fx is in the X direction and this X direction is parallel to the length of the cylindrical tube, so it will be delta L and its value is 0.1 mm. Now we have to calculate what will be the amount of, what will be the stress, strain, Young's modulus, and decrease in its diameter. So for calculating the decrease in its diameter, we will use Poisson's ratio for this particular problem. How? So let me show it to you. If you are able to understand this problem, please go ahead and start on your own. Okay. So let's calculate stresses. Because before calculating stress, we have to calculate the area perpendicular to the direction of the force. So here force area perpendicular to it is a circle, right? So area of a circle. So pi, what is our diameter? Diameter is 4 mm, 4 by 2 square. So how much it will be? Anyone? Pi into 4,
12.56.
5.56 mm square. So stress.
12.56.
Acha, acha, okay. Sorry, I misheard you. 12 point 12.56. Okay. So for stress will be force given to us. We have calculated the area. Force is 20 Newton, 12.56. So stress will be, what will the stress value?
1.59.
1.59.
1.59 Newton per mm square. Fine. Now we have to calculate the strain. Okay. So strain we will calculate in the direction parallel to the force. Okay, that is in the x direction we'll calculate. That is why I'm using subscript x. So here change in the length is given to us. Total length we also know. So it will be just the ratio of that. Change in length is 0.1 mm divided by 100, right? So strain will be 0.001 no unit. Okay, it is a unitless quantity. Fine. Everyone got the value of strain in the x direction. Now, we know, so here stress is also that we calculated is in the x direction. So using these two values, we'll be able to calculate the Young's modulus, which is stress by strain. So just the ratio of these two. So E is equals to 0. Sorry, not 0.1590. Okay. Is it, is every one of you is getting similar, around similar answer? Elastic modulus is 1590 Newton per mm square. Great. Now we have to calculate what is its decrease in its diameter. For that, we have to take the help of Poisson's ratio. So how will you define Poisson's ratio for this particular object? So the perpendicular direction, say, is the z here, which is the radial direction. Okay, I'm assuming that you can take y as well as a radial direction, but let's work with one, x and z. So it will become epsilon z by epsilon x, and we know it is equal to 0.6. It is given to us. Poisson's ratio value is given to us, and we know the value of, we've calculated the value of epsilon x. So what will be the value of epsilon z? It will be nothing but 0.6. So this is negative. Okay, 0.6 into 0.001, that is minus 0.00. Okay, there will be three zeros. Okay, right. So that will now Ez becomes negative 0.0006. This is the strain experienced in the z direction, or maybe the radial direction of the tube. Now from this, we can now calculate the change in diameter or change in radius. So how will we do that? Ez we can define, or the strain in the radial direction we can define as delta R by capital R, or we can write as delta D by capital, or capital D. Better to use the same sign or same convention of definition. So delta D we have to calculate. We don't know delta D. So delta D is del Ez epsilon z into diameter, the original diameter of the tube. So Ez we know it is negative of 0.0006 into our diameter was 4 mm. Okay. Now what it will become? Just 6 into 4, 0024. So delta D is this much. So why negative is important here? Because why we are trying to show that this much of the diameter has decreased. Okay. So now if you were to ask the final diameter, you will just like take the diameter, it is I think 4, no? 4 mm minus this value, this particular value, minus uh, 0.0024. Then you will get the final diameter of this particular tube that it has got in presence of a tensile force. So let me check if these are the correct values that we have got. So stress is correct, strain is also correct, close to correct. E value is close to correct value that we have got, and D is also correct. So were you guys able to solve it with me and got the same values? Because here the calculations were pretty simple. The understanding of the concept was important. Okay, since we have not like we have less time now, I'll go a bit faster. But in case you guys think that I'm going a bit faster, you guys can stop me and okay, I'll again go slow. So now I would like to introduce to you two key concepts for a class of material called viscoelastic materials. So there are materials which behave like a spring as well as they behave like a piston. Means they like in presence of a force, they are like elastic object as well, and as well as they are like a liquid with viscosity. So when these two are combined, those type of materials are called viscoelastic materials. Polymers, most of the polymers are viscoelastic materials. And for viscoelastic materials, we define two important characteristic. One is the creep, another is the stress relaxation. So if a piece of polymer is under some constant load, your load is constant, means the amount of stress generated in it is constant. But in presence of that constant stress, the length is decreasing, or sorry, length is increasing. Okay, change in length is increasing. Then in that circumstance, we call that particular phenomena as creep. So this particular graph will better help you understand what I've just said. So a piece of polymer, it is under a load, and this particular load, say 20 pounds, you have given, it is constant. You are not changing that. You have given once and it is constant. See that it is constant. But in presence of that constant load, your strain, the change in length, it is in like increasing. So here in this particular figure, you will get a negative sign. Okay. So similarly, it can means strain is exponentially increasing, not just increasing linearly, it is increasing exponentially. So this is called creep. What happens in stress relaxation? You're given a piece of polymer. Now you have fixed, now you're observing that the strain is not changing. Means this is your polymer. Okay. The length of the polymer is same, but the amount of stress generated in it over time, it is decreasing exponentially. Now again note, stress and strain, stress relaxation and creep, these are both time dependent phenomena. That is why you get x-axis as time. Over time people observe this phenomena on a viscoelastic material. Okay, so in one case, in creep, under constant load, the strain of the material is increasing over time. Okay, whereas in stress relaxation, at a constant strain, the length is not increasing. The internal stress generated in the material is exponentially decreasing over time. And this type of phenomena is shown by viscoelastic materials. So why we are concerned with viscoelastic materials in the first place, like why we work with it. So the yes, our tissues have viscoelasticity. Okay, and nowadays, for tissue engineering, I'm trying to explain, most of the artificial tissues are made out of polymers to mimic that particular characteristic, viscoelasticity. Okay, that is why we are that is why like I'm trying to explain what is stress as creep. Okay, polymer has become a very, very important class of material when you are going to use it to make an artificial tissue to mimic the property of the inherent organ or tissue in our body. Okay, and when you're trying to explain its mechanical properties, then you can't just rely on elastic properties. You have to go towards viscoelastic properties as well, and in under that you have to understand how the creep is happening or how stress relaxation is happening in it. Okay, now this is a question given to you on stress relaxation. Okay, so you have to calculate here. So you are given a guide tube, maybe a polymer, and onto that a fixed stress is applied. Okay, now a fixed stress is applied initially. So let me write it as sigma naught. Okay, and this value is 2.1 megapascal. Now because of this stress, some increase in length has happened. It has stretched from 1 centimeter to 1.1 centimeter. So initial length was L naught, final length was 1.1 centimeter. Now stress relaxation is a time dependent phenomena. That is why we are going to think in terms of the time is also a important variable in it. Okay, so after 2 hours we see that this particular guide tube, the stress generated by this particular guide tube has decreased. Okay, it has decreased. In stress relaxation, what we see, strain is constant. See, amount of strain that you can calculate from this value has been constant for 2 hours, but the stress has declined. What is now the final stress? It is 1.5 megapascal. Okay, now I have to calculate what is the stress relaxation time in hours. Now note from the graph that this is the exponentially occurring phenomena. Okay, so exponential terms will come when we are trying to calculate the stress relaxation time. So from the lectures, we know the expression, that is final stress is equals to the initial stress that it experienced into e to the power minus t. Okay, now t is the variable term. Okay, how much longer you're observing this phenomena, divided by T naught. Now T naught here is the stress relaxation time. Okay, so this is the expression we'll be using to solve this particular problem. We are given this value final stress, initial stress, we are given T, means time period under which the material is in observation. We have to calculate T naught. So what we'll do, we'll just first we'll put the values into e to the power minus 2 by T naught. So simple maths, nothing else. It's quite direct actually. Okay. So to remove the negative sign in the exponent and to make our life easier, I have done this particular step. I hope you guys are able to understand. Then to remove the exponent e, we will take ln as logarithm with base e, make it in a linear form, right? Let me go to the next slide. And T naught will become 2 by ln 2.1 by 1.5. So here this quantity will be in hours because this is hours and the quantity megapascal in this case is getting removed due to ratio form. So someone calculate this and tell me the value of T naught. Have you guys done it? Simple, take out a calculator and put the values and let me know the T naught value. How many hours you're getting?
0.59.
0.59. Okay. Is everyone getting this value? Others who have done it?
Ma'am, 5.9 I'm getting.
Okay. 5.9.
5.94.
5.94. Okay, so 2 against 1.
Point
So maybe, huh? Yeah. You're also getting what?
6.60, man.
6.60. Okay, fine. 6.60. So,
Ma'am, 5.95.
5.95. Okay. So these three values close by. Let me see what's the answer then. So yeah, the value is 5.9. Some of you have got 6.6, but I'll still consider as correct because it is close. Okay. So who has got 0.59? Maybe check again. Maybe some decimal error is there in for you. Okay. The correct answer is 5.9 hours. Now, for this particular question, I didn't go into much detail of how we came to the formula and all, because this particular type of topics are taught in a completely different subject in detail, that is called polymer science, because polymers are viscoelastic material and there they do thorough like studies of how the polymer is deforming and all. So if any one of you have any particular query related to how this formula came and all, maybe you can post it in the forum. I'll look it up and discuss, like give you an answer, try to give you an answer in the forum, and maybe bring it up in the next discussion session as well. Now, this is another question in front of you. This is slightly different from the one we just saw now. Okay, it is slightly different. Here, we are talking about uh, creep, okay, creep phenomena. So there is a suture. Sutures are usually made up of polymers. So it is stretched with the tensile force. When the stress is released, this value of strain has recovered by 35%. So no, it is not a creep problem. It is slightly different problem. Okay. So just go with the problem, whatever it is saying. I was wrong initially. So there is a suture. It is stretched with a tensile force. Once the stress is released, some strain, the whatever strain has generated, it recovered back. Okay. And this recovery was seen after 5 hours. You have to calculate how much retardation is there in hours, means retardation time you have to calculate. Also, you have to calculate the amount of strain recovered in say 6 hours. Here you have to calculate for 5 hours, and then after you have got some retardation time value. Using this value, we have to calculate the amount of strain recovered in 6 hours. Okay. So for solving this particular question, you will refer to this particular formula, which is comprising quantities like strain. Okay. So there is some initial strain, some final strain. So we are not given the exact values. We are kind of given a ratio. Okay. Now epsilon is equals to epsilon naught into 1 minus. So this particular is a polymer. This and the tendency to recover, it happens exponentially, right? That is why an exponential term comes into picture. And e to the power, here e to the power will become minus t by lambda. What is lambda here? Lambda is the retardation time that we have to calculate in part A. And T we are given, T here is 5 hours. Okay. So we don't know the initial strain, neither the final strain. We are given a kind of a ratio. So which is epsilon by epsilon naught, and that is coming out to be 0.35%. So 35 by 100, 0.35. You can express the percent in form of single value, and this is a ratio. Then it becomes a ratio of final by initial. So now the values seems pretty similar, like clear to you now. Now you just have to put these values to this particular formula to get the value of lambda. So 0.35 is equals to 1 minus e to the power minus 5 by lambda. So let's simplify this. Will become 0.65, correct? Then remove the negative sign from the exponent. For that, I'm taking as a ratio. Then to remove e and convert to linear form, I will use ln, and lambda will become 5 divided by ln 1 by 0.65. So what is lambda then? Someone do the calculation in your calculator and let me know what is the value of lambda.
11.62.
11.64. Is everyone getting this value of lambda?
11.60, ma'am.
60. Okay, close by. Anyone else getting anything different? Okay, so I'll assume that you are getting this, every one of you is getting the same value. Let me check the answer then. So yes, 11.6. Okay, 11.6. So that is correct for lambda. Now we have to calculate the strain value, amount of strain recovered in percent. So basically we have to calculate this ratio, lambda epsilon by epsilon naught. We have to calculate this now. So you will again use this formula only. Will rewrite here for my own convenience. So this quantity we have to calculate. Okay, this particular quantity will become equal to 1 minus to the power minus t. So in this part B, what is t? T is 6 hours. Okay, 6 hours. What is the value of lambda? Just now we have got. Now see, lambda will not change. Logically, lambda will not change for a particular type of material. If say PVA, polyvinyl chloride, you're made a tube out of it, it is like a retardation time of say 11.6 hours. Then no matter how long you check it, means say after 10 hours, 12 hours, it will stay same. It's like a unique thing or signature of a particular type of material. Okay. So the lambda will become 11.6. So we have to calculate So one side we know the values, another side we have to determine. So someone do the calculation and let me know how much are you getting. Do this, just simply put in your calculator and let me know the value. Have you done it? How much are you getting?
Point four zero.
0.40. Okay. Don't don't
0.
sound very confused. Say with confidence. Come on. Okay. Sorry, I interrupted. Who was saying?
0.40.
0.40. Okay, fine. So, anyone else getting anything different? Okay, I'll go with the fact that every one of you is getting the same answer. So, since we are asked in percentage form, then it will become around 40% amount of strain will be recovered if we are like looking at the material after 6 hours. So let me see if that is correct. So yeah, 41%, 40% is close by. So the answer you guys are getting is correct. So have you guys understood how these two problems are solved? The formulas that we are using. Again, if you have any like concept particular related to these two problems, like if you're not able to understand how the formula came and all, just if you're curious to know about it, maybe look it up. Means try to look it up. A suggestion would be that it will be much faster way to learn it. If you're not understanding something, maybe post it in the forum. I'll try to answer it like with as much satisfaction as possible. Okay. Okay. So yeah. So this is the last question for today's like session. So the question says that there is a polymer biodegradable that degrades in presence of some enzyme maybe. So it is biodegradable polymer. Its molecular weight has decreased from 10 to the power 5 to 10 to the power 4 in 200 days. Okay. And in a first order manner. Means first order kinetics has been followed. So if you remember from chemistry, the equation of first order kinetics in exponential form, how we write it, we used to write it the rate of the reaction and all. I just remember that we used to write it, the exponent was e to the power minus kt. This was there. Yes, now I remember. There was concentration, final concentration and initial concentration. So this is how we used to write the kinetics of first order reaction. So A is the final concentration, A naught is the initial concentration of a substrate, means reactant, okay, and K was the rate constant here, and T is the time over which we are observing this reaction. So similar kind of expression we will have to formulate for this particular problem as well, because it is said here, first order manner, it is degrading. So kinetics is happening in first order manner. Similar kind of expression we will formulate. So uh, first, then in that case, first we have to obtain the value of rate constant. Once the rate constant is with us, then we can answer the next part, that is the molecular weight after 400 days. Okay, so then we can, so if I'm writing molecular weight at W, then at 400 days I'll be able to calculate. First we have to find the rate constant, and then we'll be able to find the answer that they're looking for. So instead of writing as concentrations, let me write as W as the final weight, that is equals to W naught as the initial weight, L to the power minus KT. Okay. Now W final one we know is 10 to the power 4. So it has degraded, no? So final one is lesser. So from 10 to the power 5 to 10 to the power 4, it has degraded. Its molecular weight has decreased. Initial was 10 to the power 5. And it has to be multiplied with the exponent that we have is K, we have to figure it out. Now 200 days is the time. T will be 200. Okay. So from this particular expression, we have to determine K. So here will be 0.1 e to the power minus 200 K, then 10, 200 K. Okay. Just remove the negative sign of the exponent by taking a reciprocal. Okay. Then we will take ln, convert it into linear form. Now K, the rate constant, will become ln of 10 divided by 200. So what is the value of K you are getting? Anyone?
0.0115.
0.0115. So others, do you guys support her answer? Or are you getting different answer?
0.0115, ma'am. That's
Okay,
same.
good. Same answer. Great. So others also should get this particular rate constant. Okay. So this rate constant we have calculated. So again, we will look at this particular expression. We have W. Okay, we have to figure out in the next part, we have to figure out the W value. Okay, we don't know this. We know W naught, the initial weight, we know. We now know the rate constant, and we are given the time as well. So it's pretty straightforward then. W will become W naught, that was 10 to the power 5 into e raised to the power minus K. K was 0.0115 and T was 400. Now, what will be the value of W then? Have you guys done it? What will be the value of W? Her W is the molecular weight of, huh? Yes, sorry, I didn't.
99.48 into 10 power 5.
99.48. I'll repeat.
Yes. 99.48 into 10 power 5.
10 to the power 5. What about others? Are you guys getting the same answer?
Sorry, I made a mistake.
Okay, so what is the answer you're getting then?
1 into 10 power 3.
1,000 basically. Okay,
1005.
1,005. Okay. What about others?
1005.
Okay. So let me check the answers now. Yes. You guys are like have done it correctly. The molecular weight after 400 days that the polymer will have is 1,005. Okay. Okay. So that's it from my end. Okay, someone is mute. Okay, I've muted that person. So that's it for today's session.
Ma'am,
Yeah.
can you show the steps in between, like you showed before how to do logarithm, exponential to logarithm. So only how this 1005 answer can.
Okay. Okay. So good. Good. You should tell. Okay. So what others have done and what you should do. First, you have to remove the negative sign. So sorry. To do that, you take reciprocal. Now you just calculate this part, this exponential part. So let me do it. What we are getting 0.0115 into 400.
4.6.
Yes, 4.6. Now 4.6. Now in your calculator only you will get E. Okay. So find that and give it a exponent of 4.6. Then you will get 99.48. Now you divide these two values. So 10 raised to the power 5 divided by 99.48. So it is coming out to be 1005.2. Okay, 2324. Okay, whatever. So this is how you should approach when you are given an exponential component in your expression. Now, is it clear?
Yes, ma'am. Thanks.
Great. So, as I was saying, that's it from my side for today's class. If you have not understood anything that we have discussed in last 2 hours, feel free to raise your queries. Okay. Those who have joined late want me to repeat something because they joined late. They can also like tell me. Maybe I can repeat some of the concepts that I discussed today. And if there is additional problem that you're facing with the week 2 content after this class, maybe you can post it on the forum. I'll try my best to go through those queries and answer it there only. Otherwise, I'll take it up in next week's session as well. I hope today's class was productive for all of you. Okay. I hope only you guys can answer that anyway. So any queries from any one of you?
Ma'am, if you don't mind, can you explain that Poisson's ratio again?
Okay, I will. So the definition of Poisson ratio, in the definition of the Poisson ratio, the direction thing is there. Okay, you have to look at the direction first. Keep that in mind. Next, it is a ratio of two strains. Now, one strain is in the direction perpendicular to the applied force, and it is divided by the value of strain which is parallel to the applied force. So you are given an object. You are told that this object is experiencing force in, say, in this particular diagram, in z direction. All right. So then in this case, what the Poisson ratio will become? It will become a ratio of strains. First, ratio of strains. Upper numerator will be the strain applied in the or experienced in the perpendicular direction. Means if z uh, is the like direction of the force, then the perpendicular to z is x. You can also write it as y. Y is also perpendicular to z, divided by the strain experienced in the parallel direction of the force. So here the force is in the z direction, then the denominator will become epsilon z. Similarly, you can write these two expressions. So here is a 3 coordinate. No, that is why I forgot to mention previously that x is there. So if you have x and y only, then this particular definition is accurate. If you're given z and y, this is how you will write the Poisson's ratio. You cannot write as in form of x and y, because in x and y direction the force was not applied at all. You have to look where the force was applied on the object. Accordingly, you have to define Poisson's ratio. Okay, is it clear? Numerator 1 is for the strain perpendicular direction. Denominator 1 is the strain in the parallel direction. That's it.
Yes, ma'am. Thank you.
Yeah. And negative sign also you should remember. Why negative sign? I think you can understand, right?
Yes, ma'am.
Anything else from anyone? These notes, this recording will be available to you. Okay. So you guys can refer it later on. And if any other queries you have after the class, you can post it in the forum as well. I'll try to answer it as much as possible. Is all of you going to give the exam for this course?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
And like who all attended the first week session? Okay, 1, 2.
I have attended, ma'am.
Okay, 3. Okay, many of you are coming again, so maybe I'm teaching something right. Yeah, okay. So I hope that you guys keep coming for whole 8 weeks, and it will basically boost up my confidence as well as a instructor here who is trying to convey some concepts. So it will definitely boost up my motivation to prepare well. Yeah.
Sure, ma'am.
Sure, ma'am.
So if no other queries, then maybe we can like meet again in the next week. Okay, on Saturday from 4 p.m. and we will discuss week 3 content. Okay, but if you have any queries related to week 2 content as well, you can bring it. Okay, we can towards the end of the session we can discuss those queries as well. If week 2 is difficult for some of you, okay, you guys can definitely do that. And later on, towards the end of the course, there will be one revision session as well where we will revise all the content. So don't worry if you are lagging behind. So in the revision session, your doubts will get more cleared in this live session format. Otherwise, you can anytime you can pose your queries in the course platform, like ask me question. If you click ask me a question in your tab, it will directly go to the Google group. Okay, where you have to just type it out. You have to have a Gmail account to raise a query. You just sign in with your Gmail and you will find a Google group. You just have to type it. Many people are doing it actually. So those of you haven't and have queries, you can try that. It's like it is like a direct way of communicating with us, with the TAs who can help you directly. Okay, so you guys can leave the meeting. I'll share the recording and I hope to see you all next week. Bye.
Bye, ma'am.
Thank you, ma'am.
Thank you, ma'am.